Okay, so welcome everybody. Sorry for the technical hiccups. So today it's a pleasure to have Simona Pacuraru from the University of Birmingham. She's doing a PhD there with Clement Bonnerò.
Yes.
Before she did her master at the University of Milano Bicocca, and she talks about things we know nothing about, so tidal disruption events, and hopefully she will give us a nice introduction to the topic. Thank you, Simona.
Thank you. Yes, so today I will talk about tidal disruption events. Oh my God, is that? Tidal disruption events, and so in the first part of the talk I will try to give a general introduction on TDs, and then in the second part I will talk about my research, and in particular about how magnetic fields can affect the evolution of a TD. And I will start with some motivation. So a tidal disruption event happens when a star gets disrupted by the strong tidal pull of a black hole residing in the center of a galaxy. And during this event, a luminous flare of radiation is produced, which we can observe. And one of the main motivations for studying TDs is that we can use these observations. We can use, there is a notification, I think, but, yes, I have to do a METI. But it doesn't work. The cursor doesn't work. There is someone. Okay. So we can use observations of TDs to measure the masses of black holes, and therefore to learn also something about their origin. And to explain this, I will show here on the right a sketch of the black hole mass function. Just a moment. Okay. So this is a sketch of the black hole mass function, which describes how many black holes we have for a given mass. And at high masses, this is well constrained from observations of quasars at high redshift and from dynamical measurements in the local universe. However, at around 10 to the 6 to 10 to the 7 solar masses, black holes become much more faint and much harder to detect. And so there we cannot rely anymore on observations. But there are ideas of how the black hole mass function might look like, depending on the black hole seed formation channel. So one idea is that seed black holes were formed from the collapse of population-free stars. These are the first generation of stars in the universe. And in this scenario, we expect the black hole mass function to rise towards low masses. But there is another channel, the so-called direct collapse channel, where instead black hole seeds are formed from the rapid collapse of massive clouds in the early universe. And in this case, the black hole seeds are much heavier, and that's why we expect the black hole mass function to drop towards low masses. And so why are TDs useful? So as I was saying, a TD happens when a star gets disrupted by the tidal pull of a black hole, and for that to happen, the star needs to come close enough. However, to the black hole, but there is a limit on how massive the black hole can be. In fact, if the black hole is too massive, then its event horizon will be so big that the star will cross the horizon before you can see it being pulled apart. And so in that case, the event is not visible. And this limit for a main sequence star is at around 10 to the 8 solar masses. So below 10 to the 8 solar masses, we can see tidal disruption events. And that's why TDs can help to probe the lower end of the black hole mass function, and therefore to learn something about the origin of these black holes.
So if the black hole is too big, the star is just swallowed
directly, yes.
As a whole, without being disrupted?
Yes.
Okay.
Mm-hmm. So there is another reason why TDs are very interesting to study. And this is because, as I will show in a moment, during a TD we expect an accretion disk to form around the black hole. And TDs are quite unique in this because I will also show that they happen on human timescales. So in principle, one can see the full life of the accretion disk starting from its formation. And so by studying TDs, we can also learn something about other astrophysical accretion disks, like for example, those of AGNs. And there are many other physical processes that are common to other systems. One of them is magnetohydrodynamics, which I will eventually talk about today. But before that, I want to give an overview about both observations and the theory behind the TDs. And I will start with observations. I don't do observations, so this will be very simple. So the main observational features of TDs is that they are mainly observed in the UV optical band, and the light curves are featured by a very fast rise to peak luminosities in between 10 to the 43 to 10 to the 45 ergs per second. And after the peak, then the luminosity decays smoothly. Some TDs are also observed in the X-ray band, but here the light curves are much more variable. They have similar luminosities to the UV optical band, typically, with some exceptions. So you can see the stars in this plot have the light curves marked by the stars have much higher luminosities. And these, in fact, are typically interpreted as coming from a relativistic jet that was launched during the event. Then they are also observed in the radio band, and here there are mainly two populations based on how luminous they are. So TDs with very high radio luminosities are interpreted as coming from on-axis jets, while those that have lower luminosities are interpreted as coming from either off-axis jets or non-relativistic outflows. And we have seen roughly 100 of these events so far. And with the upcoming survey LSST, this number is going to grow by roughly 2 orders of magnitude. However, to be able to use these observations to constrain the properties of black holes and the properties of the TD, we need a robust theoretical model for these events. And so now I will try to talk a bit more in detail about what we know about TDs from a theoretical point of view. So the possibility that a star could get disrupted by a massive black hole at the center of a galaxy was suggested even before TDs were observed. And the idea is that they originate from stellar gravitational encounters happening in the center of galaxies, which can occasionally launch a star very close to a black hole, the central supermassive black hole. And when this happens, the star can fall below a critical distance that is called the tidal radius, where the self-gravity of the star, which was keeping the star in hydrostatic equilibrium until then, becomes weaker than the tidal force exerted by the black hole. And what the tidal force does is to impart a spread in orbital energy across the star. So the center of mass of the star will keep orbiting on a zero energy trajectory. However, the half of the star that is closer to the black hole gains negative energy, and so it becomes bound, and it starts orbiting on elliptical trajectories, while the half that is farther away from the black hole will gain positive energy and will start traveling on unbound trajectories. And so because of these different trajectories, different parts in the star will travel on different time scales. So we can imagine that the most bound fluid element eventually will have reached this red cross. But a less bound fluid element that is on a slightly wider orbit will be a bit delayed. And so on. And so on for the rest of the gas in the star. And so you can see that because of all these different trajectories, the star gets stretched into an elongated stream, and half of it is bound, so it will eventually return back close to the black hole. So the evolution, the hydrodynamic evolution of the stream during these early parts of the evolution is quite well understood. And one of the main analytic predictions, which has been confirmed by numerical simulations, is that the rate at which the mass in the stream comes back goes like time to the minus 5 third times a term, this dm in d, which describes basically how the orbital energy is distributed across the star. And this prediction has quite a long history, because when TDEs were observed for the first time, they were seen in X-rays, and they seemed to agree with this decay. So it was believed that that these flares were coming from an accretion disk, because an accretion disk at the scales of the tidal radius is expected to emit in X-rays from standard accretion disk theories. And also that the luminosity coming out of this disk was tracking this fallback rate. And this expression has been used for quite a long time to fit the light curves of TDEs and to get out the mass of the black hole and the other properties like the mass and the radius of the star. However, it turns out, as I was saying, that actually TDEs are mostly observed in the UV optical band, and this cannot be explained simply by an accretion disk. So some other mechanism needs to explain the light coming from these events. And this has something to do with what happens to the stream next. So what happens after it returns back to the black hole. And so while the early evolution is quite well understood, when the stream comes back, the evolution is much more uncertain, and that's because the stream gets compressed a lot at its closest approach to the black hole, and the problem becomes computationally very, very expensive. And to illustrate this, I will show you this movie that I did at the beginning of my PhD. This was my first simulation. So I don't know if you can see, this is the star, this pink dot. And it's on a parabolic orbit. So if I start the movie, you can see that it gets stretched into this stream. The center of mass keeps going on the parabolic orbit, but the half of the stream that is closer, it starts coming back. And what you will notice is that the stream gets stretched so much that you can see the particles one by one coming back. And this is a problem because so in a particle-based hydrodynamic simulation, the resolution is set for each particle taking a circle that contains a few tenths of the neighbors. And so you can see that here the resolution is bigger than the local size of the stream, and that will affect the evolution. There will be numerical errors.
What is the physics here in this simulation? There is a hydrodynamics, or it's just ballistic particles?
No, this is hydrodynamic. It's a hydrodynamic simulation.
Okay.
Yeah.
So it's SPH?
Yes, I use Gizmo. Okay. Yeah, but yeah, it's a particle-based simulation. Yeah. And so this is quite an extreme case. Meaning that in reality nowadays simulations can follow the return of the stream and see the vertical collapse. However, this problem will be there when the stream will reach the closest approach to the black hole. And the reason why this problem is so computationally expensive is that the stream is expected to be compressed down to 10 to the minus 2 to 10 to the minus 3 solar radii, while its longitudinal extent is of 10 to the 4 to 10 to the 5 solar radii. And so you need to resolve like 10 to the 6 order of magnitudes, which has never been done yet, in the sense that there is still no converged 3D simulation of this part of the evolution. So this is uncertain, but we can go on and assume that this compression is not gonna significantly affect the evolution. And what we know will happen next is that because the stream approaches the black hole so close, general relativistic effects will be important, and in particular the stream will precess, and it will self-intersect at this point. And here we will have a collision between the two streams, and because, as I said, because we don't really know accurately what is the outcome of this compression, it might be that the collision will happen at different distances from the black hole. But the main point is that this collision between the streams can dissipate energy, allowing the gas to eventually circularize into an accretion disk. So people have been trying to simulate this event, also by trying to circumvent the computational problem. And I will give you some examples of how people have been doing this. So the one possible approach to the computational problem of simulating a TDE is to divide the TDE in different parts, temporal parts, and to study the different parts locally. So for example, on the left, it's simulation where they omit the stellar disruption and they only simulate the stream infall towards the black hole, and so they have to assume something about the stream, while here they study a later part of the event where they only simulate the basically they simulate the outcome of this collision to see how the disk could form from that collision. And then the other way is to just run the full TDE. And of course, this has the advantage that you don't have to make any idealized assumptions, meaning that you can just start with a star. But of course, on the other side, the resolution will be poor, and therefore the results might not be as robust. But so there is a lot to do, meaning that the simulations need to improve. But what has been understood so far, or at least what the simulations agree on, is that eventually an accretion disk forms, and also this accretion disk or the full evolution can reproduce the volumetric luminosity that we observe. But there are still many questions that are open, and in particular on the multi-wavelength features of these events. And the main question that still needs to be answered is how is the UV optical light produced during a TDE? And not only that, also how exactly energy is dissipated during this collision, and how the gas is able to circularize into a disk is still an open question. And there are two main ideas for what could answer this question of how UV optical light is produced. One idea is that shocks are responsible for this for the UV optical light, and in fact, when the stream collide, a shock is produced, and a shock can convert kinetic energy into thermal energy, and that can also happen when after the disk has formed, the stream will be still coming into the disk, and the interaction between the disk and the stream can also produce shocks, which can be then convert kinetic energy into thermal energy that can be emitted into radiation.
So the volumetric luminosity is explained by the combination of the accretion disk and the collisions, or just by the accretion disk?
I don't know exactly, but I think the accretion disk mainly.
Okay, so the UV optical, if it's the shocks at the collisions,
yes,
like they don't contribute a lot.
I think they don't contribute a lot. So I don't exactly know all the results of these simulations. So what I know is that for sure, if the stream was to remain quite thin, then it's expected that the emission during the self-crossing shock is not going to be very radiatively efficient, because because the streams are so thin, they will be very optically thick, and so they will be very dense and so very optically thick, and so it's going to be relatively inefficient. While if the stream was going to be much wider, then that could make the process more relatively efficient. But I think it's uncertain. I don't think it's...
And the accretion disk, is it the same? I imagine that around every black hole there is some, at some level there is an accretion disk. Is this an accretion disk? So the stream is fueling the pre-existing accretion disk, or is forming a larger accretion disk which is a bit different? I don't know.
So it's not a pre-existing. This disk is formed during the TD, but what I think is that you form this disk, but then you still have gas that like is orbiting on much longer timescales. It still needs to come back, and eventually it will inflow into the disk. Yes.
Do you have an estimate about the timescales necessary to circularize the accretion disk? Is it a function of orbital parameters, mass?
I don't remember.
Okay.
Sorry.
And, sorry, you said the mechanism by which the accretion disks form is unknown, but simulations agree.
Yeah. So the idea is that at the stream-stream collision, an outflow will form from the collision, and some gas in this outflow will be bound, and so it will start to circularize. And this is a result that has been found in some simulations.
By relaxation?
Sorry?
By which mechanism it circularizes?
It circularizes because the stream collision dissipates energy.
Okay.
So that will allow to initiate the circularization. But so I think in some simulations have found that after the outflow is launched and the gas starts to form the disk, shocks happening in the disk further dissipate energy, and eventually it circularizes. I think some simulations also find that you get eccentric disks, so they don't fully circularize. But yeah, this is has not been the focus of my research specifically, and that's why I don't know all the details. Sorry. The point is that I think different simulations find different results, and so that's why it's so uncertain, because there is not yet a common agreement for what could answer this question. Any other question? Is it clear?
Yes, no, sorry for interrupting.
No, it's okay. No, you can interrupt. It's not a problem. So I was saying that one idea is shocks. Then the other idea is that actually the light is produced by the disk, and it is so the disk produces X-rays. However, maybe we have some layer of gas that is outside of the disk that is maybe produced during the TDE, and that could reprocess the X-rays such that we can see the just UV optical. So we want to be able to answer this question because that's what we need in order to improve models of the light curves of TDEs, which then can be used to, for example, to measure the masses of black holes. And to do that, we need to not only advance the simulations, but also incorporate into the simulations some physical effects that are often neglected, but which we know that are there and that can have an impact. And so one of them is magnetic fields, and this has been the focus of my PhD so far. So trying to answer the question of how magnetic fields can affect the evolution of a TDE. So why magnetic fields? So the magnetic field that I will be talking about is the magnetic field of the star. In fact, stars typically have magnetic fields, And if they get disrupted, the magnetic field will participate in the evolution, and it can potentially affect it. And in fact, we know that during the stream evolution around the black hole, the magnetic field can become dynamically important, and this is expected to cause a fast increase in the stream thickness. And this can have different consequences. So for example, we know that the unbound part of the stream, this is the one that escapes the system, this will eventually interact with the ambient medium, and the interaction between the ambient medium and the unbound tail can produce synchrotron radiation. And having a thicker stream can increase the synchrotron radiation, and this could potentially explain the radioluminosity that is observed in some TDEs. Instead, the bound part of the stream, as I was saying, when it comes back to the black hole, it precesses, so it causes, it leads to this stream-stream collision. And here, having a thicker stream could affect the hydrodynamics and so also the radiative efficiency of the shock. And so this will eventually affect also the formation of the disk. And here, regardless of how important magnetic fields are during the earlier evolution, here magnetic fields may play a crucial role because they are known to provide the viscosity that powers this disk through the so-called magnetorotational instability. That is a mechanism that allows to transport angular momentum through the disk, and so to allows the gas to accrete. There are other reasons why magnetic fields can be important during these last stages, and one of them is that strong magnetic fields could support the disk against thermal and viscous instabilities. The other reason is that strong magnetic fields could power relativistic jets through this Blanford-Nayek mechanism. And so I have been focusing on the early part of the evolution, so until the stream comes back to pericenter or near pericenter. And I've been using both simulations and the semi-analytic model to characterize the magnetohydrodynamic properties of the stream. And so the reason why we cannot study the full event is, as I was saying, is the computational problem. But I want to emphasize that to be able to study these last stages of the event, where most likely most of the light will be produced, we need physically motivated initial conditions, and that's basically the goal of my project. So before talking in detail about what magnetic fields do during a TD, I will give very quick summary of what we know about the hydrodynamics, and which is, as I was saying, is quite well understood. So what we know is that as the stream moves away from the black hole, the elongation grows like the distance to the black hole square. And this scaling is due to the tidal force exerted by the black hole. Instead, along the transverse size, in the densest parts of the stream, the gas is maintained in hydrostatic equilibrium, and that's why, and because of that, the width follows a slower scaling, r to the 1/2. However, in the more dilute parts of the stream, what dominates the dynamics is the tidal force, and that causes a faster evolution. So that's why you can see that the stream has different thicknesses. So this picture, what I will show in this talk is that this picture is going to change when we include magnetic fields, or it can change when we include magnetic fields. And to show you how magnetic fields evolve during a TD, I will start by showing one of my simulations. So as I was saying, I use Gizmo to run the simulations, The simulation is initialized by taking a star that is modeled as a polytrope, and this is put on a parabolic orbiter on the black hole. So what you can see here in black are the magnetic field lines, and we explored different geometries. In this case, you can see a magnetic field that is toroidal and in the orbital plane. And the movie is in a frame that is co-moving with the center of mass of the star. So you will see the center of mass of the star fixed in the movie. So if I start the movie, and if you focus on the magnetic field lines, what you will see is that they reorient, and eventually the dominant component of the magnetic field is the one in the longitudinal direction, so in the direction in which the stream is stretched. And this is quite important, so I'm going to explain why this happens by approximating the stream to be a cylinder which elongation and thickness evolve in time. And we can imagine that the magnetic field is not aligned with the direction of stretching initially, but we know how the magnetic field is going to evolve, because in this study we make one important assumption, that is the ideal MHD assumption, which implies that the magnetic flux must be conserved during the whole evolution. And because of that, so magnetic flux conservation tells us that both the components of the magnetic field need to evolve in such a way that they are inversely proportional to the area that they are going through. And so we know how this cylinder is going to evolve. As I was showing earlier, it's going to expand in both directions, so both the stretching direction and the transverse one. However, the stream is stretched in the longitudinal direction much faster than in the transverse direction, which means that the vertical component of the magnetic field will be suppressed much quicker. And so that's why the magnetic field eventually aligns with the direction of stretching. And so this alignment is crucial because that's one of the ingredients that eventually allow the magnetic field to become dynamically important. And to explain this, I will use again this picture of the cylinder, focusing on the part of the stream that is denser, so the one that is initially maintained in hydrostatic equilibrium. So when we do not have magnetic fields, the stream is in a balance between self-gravity and gas pressure force. When we include magnetic fields, the main effect is that we will have the magnetic fields act as if there was an additional pressure. And so we are interested in knowing whether this new pressure term will eventually become the dominant one. So we can look at how magnetic pressure evolves. So magnetic pressure is given by, is proportional to the magnetic field square, but we know how the magnetic field evolves. And in particular, we know that eventually it aligns with the direction of stretching. And so it must go like 1 over the width square. But we know how the width evolves with distance because of hydrostatic equilibrium. We know that the scaling that we expect is h going like r to the 1/2. Plugging in everything, we see that magnetic pressure is expected to drop as the stream moves away from the black hole. And so you might think, oh, how do we get to make this magnetic field dynamically important if magnetic pressure is dropping? The key is that we also have gas pressure, and this also decreases because the stream is stretched. However, it decreases much faster, and therefore eventually magnetic pressure can become dominant, and that's when we expect the evolution to deviate from the hydrodynamic one. So we looked for this effect in the simulation. So here you can see the whole stream at some time after the disruption, and in the hydrodynamic case, and you can see that the stream is quite well confined by self-gravity. If we include magnetic fields, actually a strong enough magnetic field, the stream is by eye much thicker. And so we quantified a bit in more detail how the width evolves along the stream by slicing the stream in different sections based on their orbital energy. And for each section, we calculate the width. So here, I show the result. So on the y-axis, we have the width, and on the x-axis, the distance from the black hole, which you can also think as time. This is, in the end, it can be thought as a temporal evolution. And here I start showing the result in the case where we do not have magnetic fields, and for a parabolic stream section. And as you can see, the width oscillates around the expected scaling from hydrostatic equilibrium, so r to the 1/2. Instead, if we include magnetic fields, the evolution eventually deviates. That's when magnetic pressure becomes dominant. And when magnetic pressure starts dominating the dynamics, because of this fast expansion, actually the magnetic force suddenly drops. And so for some time, the stream is not affected by any force. And so it expands at constant speed, which is what gives this r to the 3/2 scaling. However, this does not last forever. In fact, as the magnetic force decreases, eventually it approaches the tidal force. And from then on, we have an equilibrium between tidal force and magnetic force, which produces this r to the 5/4 scaling. And so here I've been focusing on the parabolic stream section, but this effect is happening everywhere else in the stream. And the scalings change depending on where you are in the stream, because the properties of the gas change. However, all these scalings can be reproduced with simple analytic calculations. And so as you can see up in the legend, the magnetic field that I have there is of 3 megagauss, which is very big. And so the reason is that you need a magnetic field that is strong enough in order for this effect to happen. There are a combination of reasons for this. The main one is that the time where this deviation occurs strongly depends on the initial magnetic field. And I have estimated analytically that in order for the magnetic field to affect the evolution in roughly half, like 50% of the mass of the stream, within a year after disruption, you need a star that has initially a magnetic field of around 10 to the 4 Gauss. And so what are the magnetic fields in stars? So this is quite uncertain. In particular, we are interested in what is the magnetic field in the core of stars. And this is uncertain, but recently there have been some studies which constrain the magnetic field in the core of stars through asteroseismology measurements. And these have found that basically by tracing back the magnetic field through flux conservation, they find that, because this can be done only for red giants, and so they use flux conservation to trace back the magnetic field, finding these values, 10 to the 2 to 10 to the 4 Gauss. Then there are some other stars, these peculiar stars, AP, BP stars, which also have can have particularly strong magnetic fields. And finally, there is this idea that in the galactic center, stars can merge, and during the merger, the magnetic field can be amplified. And simulations have found huge values for the magnetic field. But yeah, I think this is quite uncertain, and it needs to be explored in the future. But the point is that, so it is a bit uncertain what are magnetic fields in stars. So also whether this effect will be relevant. But for now, we can what we can think is that maybe we will have different populations of TDs depending on the initial magnetic field. So those where the magnetic field of the star is so weak that this effect won't be there, and so we will see just the hydrodynamic evolution, and or magnetic fields that are very strong, and in those cases we will see a deviation. And as I was saying, this deviation can have an impact on the subsequent evolution. So to be able to explore the parameter space, we also looked at this problem with a semi-analytic model. And so this model is based on a model that was developed by my supervisor, Clement. And what I did was to include magnetic fields into the model. And so how does it work? So basically in the model, the star is sliced into different sections, again, based on the orbital energy. And then for each section, that is a two-dimensional section, we solve a system of differential equations that approximate the dynamics. And one of the things that we solve for is the width. So we can look at, again, at how the width evolves with the distance from the black hole. And here I show a comparison with the simulation. And you can see that the qualitative behavior is similar in the sense that we can recover the expected scalings, and therefore the physics is the same. And with the semi-analytic model, we can also look at the evolution of bound stream elements that are returning back, which can be computationally prohibitive with simulations, especially if you consider bound stream elements that evolve on long time scales. And so with both these tools, we are able to constrain the magneto-aerodynamic properties of the stream, both the width and also the magnetic field, which I didn't have time to talk about today. Yeah, so these results, so the constraining the properties of the stream, will be useful to study the later part of this event. And in particular, what we want to know is how magnetic fields, how this effect of thicker stream and how magnetic fields in general will affect the stream-stream collision, and how the magnetic field will look like in the outflow launched during the collision, and therefore also how the magnetic field will look like in the accretion disk, and that will tell a lot about whether, for example, the magneto-rotational instability is going to develop or not. One last thing that I wanted to mention is that so the ideal MHD assumption that we do, according to this assumption, the gas must be ionized, fully ionized during the whole evolution. But in reality, we expect this to break down eventually, because the stream gets stretched, and therefore it's going to adiabatically cool down, and eventually you reach a point where the gas starts to recombine into neutral atoms. And this recombination process can inject additional energy into the stream, and this energy could be either radiated away, or it could lead to a similar effect to that caused by magnetic fields, so causing an expansion of the stream. And another consequence of recombination is that the ideal MHD assumption won't hold anymore, and so also non-ideal MHD effects need to be considered. And so this is also another project that I'm working on. So I will finish with a summary. So TDs are a powerful tool to study black holes and their origin, and I hope I convinced you that magnetic fields can be important during a TD, and they can cause this fast increase in the stream thickness, which can have consequences for the later evolution. And also by studying this, by studying the TD with the inclusion of magnetic fields, we can not only look at its effect, but also characterize the properties of the stream, which can be used then to study the later evolution of the event. And I finish, and that's it.
Thanks a lot. So if you have questions.
So you, from what I understood, the magnetic field and the magnetic pressure increases the width
Yes.
of the otherwise very stretched and very thin stream. So is this enough to maybe make it easier for for the problem of resolving with a
Yes,
simulation?
actually, yes.
So
yes,
it
does.
actually becomes if you use a gigantic magnetic field, it actually becomes not so stretched. To
You mean
simulate.
in the part where it gets compressed?
Yeah, even in near the black hole.
Yeah, so I haven't looked into that, but I think that I'm not entirely sure. But in principle, yes. If the stream is thicker, then but I'm not sure because this is something I really wonder. I don't know, but I wonder if you have a thicker stream, when it's gonna collapse, whether you expect it to get to smaller distances, because if you start from a thicker stream, the potential is bigger. So actually, maybe you are going to go to even lower distances.
Okay.
So I'm actually not sure. I have no idea.
Nice talk. Do you think that relativistic effects from the black hole could play an important role in your work, and how?
Yes, so in what I've been working on so far, so the early part of the early evolution, no. I think it does not, because in the end, the way general relativistic effects play a role is by causing this precession effect. And I have been studying only the early part of the evolution, so until the stream comes back. So yes, so in principle, if you were to run the simulation with GR, the stream, the star would precess around the black hole, but we assume the effect of GR during this part of the evolution to be negligible, in the sense that what will happen is simply that the stream will be slightly inclined, tilted. Yeah.
Can you go back to the figure with the widths
Yes.
in the magnetic and non-magnetic case? So yeah, these. Just asking about the non-magnetic case. Is there a simple explanation for the oscillations, like the time scale of those oscillations, for the parabolic case?
Yeah. So the reason why we have oscillations is because the hydrostatic equilibrium is not a perfect equilibrium, and that's because when the star approaches the black hole, the tidal force excites perturbation, which then propagates. I don't really know about the timescales. That must depend on the properties of the stream.
So perturbations.
Yeah.
But can I ask a question? In this picture here, in the semi-analytic model, each slice here is treated separately.
Yes.
But the cylinder you were talking before, it's this one. These are not the
Yes.
cylinders.
Yeah.
Okay.
Yeah. Yeah. So in the semi-analytic model, you take each slice, and each slice is a 2D section.
Okay.
So then you are evolving.
But they're almost like the section of your cylinder that you had before, or not.
Yeah. They are sections of the cylinder that I was showing. Yeah.
Ah, okay.
What is confusing?
No, sorry, because these look like little cylinders.
Ah.
Because these are not the cylinders.
Well, yeah, you can divide the cylinder in even smaller cylinders if you want.
No,
And-
okay, no, it's fine.
You have a task in your slides about 12. So there's a movie about the stars.
Yes.
This one. So here you assume like the rotation of the star magnetic field is in the same as its orbit.
Yes.
Is this the common?
No. No. So I mean, we consider different geometries to because first of all we want to start with something simple. So actually the results that I show later are for a magnetic field that is linear and so constant everywhere and or in the same direction. We explore different geometries. This is another case we have considered, but in reality the most realistic case we have is a tangled case that is a combination of a toroidal and a poloidal magnetic field. And the reason is that so we not only the magnetic field, the strength in stars is uncertain, but also the topology. And what we know from theory is that in order for the magnetic field to be stable in the star, there has to be a combination of both these components. So that's another case that I've been looking at. But actually the geometry during this early part of the evolution does not play an important role. And that's because, so in the end, in order for this effect to happen, you need the magnetic field to initially have some component in the longitudinal direction. That's because you can see if so if the magnetic field was going to be only in the vertical direction, and as the stream expands, you keep having just a component in the vertical direction. So initially you need one along the stretching direction. What is the fraction of the magnetic field initially in the longitudinal direction? That will tell how much this deviation from the hydrodynamics is delayed. But I have tried to estimate this, and the geometry does not seem to play a significant role. The most important thing is the strength of the magnetic field, the overall strength of the magnetic field.
Quick question: do you expect when the star is compressed, radiation pressure to become important?
You mean in the first passage, or the stream? The stream in the
general, yes.
Radiation pressure.
But radiation from what?
When the star is.
Because it's a star. Okay.
Yes. And when you heat up the gas, at some point the pressure
Does
from the
the
photons.
star turn off when it's stretched?
It should.
I don't know.
Not that I know. So what I know is the evolution is relatively inefficient until the streams collide. But yeah.
When you have the pressure, it's an opticalytic medium.
Yeah, like
so
when
your
you do
radiation
the
and gas
equilibrium of a star,
Yes.
Yeah.
then you also add the term with the.
Exactly.
The
Typically, the main
compression.
sequence stars, there's low mass, is subatomic.
Yeah.
It's a minute by gas pressure, but maybe when it's compressed,
Mm.
it becomes very important. I don't know.
Yeah, not that I know. Mm-mm. Yeah, I think it's usually assumed that the evolution is adiabatic and that the radiation does not play a role.
Okay, then let's thank Simona again.